Hello. Okay, can you hear me? Can you see the desktop? Does everything seem okay?
Yes, I can.
Okay, great, thanks. We set things up. Okay, still more people to come in. Okay, all right. So, so today we're going to talk about this stuff here, the perspective projection rasterization. We're going to look at the algorithms. Okay, so first, does anybody have any question about the homework assignment? Maybe you had time to start it and look at it. Does anybody have any question about the homework assignment so far? Anybody have any question about this stuff here yet?
I'm still a little bit maybe trying to figure out the post-process method. I'm kind of stuck on for the second part.
The whole you got the first animation going.
Yes.
Just yeah, you have to. I mean, the idea is that you save 10 or what is it, 20 frames at a time.
Or is it 30? Is it
30? Yeah, 30 frame. You create a list of 30 frames, and first just get that first one. Well, try to get 30 frames combined into one frame first.
Mm-hmm.
Yeah, just get, and what you'll get is if you generate 30 frames and you put them into one frame, you'll just get this black, a white streak. Yeah, because and then work on getting them to the older frames to get lighter as they go along, which creates the tail.
Okay. Yeah, may have more of like a specific problem because I kind of got that, but it's kind of like the PNW kind of gets breaking up and you can kind of see the trace, but it's not like a complete white
Oh,
streak. So
okay.
it might be
Well,
something in the earlier steps. Or maybe I thought I did right. It might be something I have to ask you in the office hours.
yeah,
That's
I mean
more
that's,
specific.
I mean, yeah, it sounds like you got the ideas, it's the details now. Yeah, the details, yeah, if something's really weird in your code, if it's not, yes, then it's just very better to send me a copy of it, and we can talk about it. But
Okay.
yeah, because it's a fairly tricky little thing to do. Like you're taking a sequence of frames, you're combining them into one frame, and then you have to advance the sequence to the next frame. You have to drop one frame, add another frame to the sequence, do that over again. Okay, so there's a lot of orchestrating of this stuff going on, but the the key thing is, can you get 30 frames packed into one frame? If you can get that, that's probably the hardest part.
Okay.
What about any question about the structure of this assignment? Anybody else? Oh, one thing I can mention, this link here is broken already. These people update their software just almost every week. So you need to download 10.30 now. So now you go up here and change that to 30, and that'll probably break in another week. It'll be 31. And the trouble with these people is ImageMagic's a really good piece of software, but they had this weird idea that they should delete the old versions from their distribution site. So like the version that I was linking to is gone now. It was there a couple days ago. It's been replaced by version 30. And unlike most other groups, they delete the older version. So they don't leave it up there. So if you click on this and it's dead, just advance the counter, go up here, advance the counter one. It might even need to be advanced a couple by the time you try it, but just go to 30. Yeah. All right. So it's a weird piece of software. It's almost hopeless to link to them. And what they don't provide, which they're supposed to, is a generic link to the most recent version. I can't find, they should create what's called a symbolic link to the most recent version. so you could always link to the most recent version. But I can't find that on their website either. I don't find a symbolic link to the most recent version. I have to look again, but it's a very good piece of software. Okay, and then after you, there's another thing you have to. There's another little change you're going to have to make. Be down the homework assignment. So if you haven't got this working yet and you're downloading it right now, you're gonna have to make one other little change. This batch file makes reference to the older version. So you have to edit it and change that 29 to a 30 also, because you'll have downloaded version 30 instead of version 29. So you've got to, you'll have to update the link and you'll have to update this path in this script. Okay, so I mean, every year that's a problem. They update their software probably almost every couple, at least once a month, and I think it's more often than that. Okay, so linking to them is kind of hopeless. That was the current version as of a couple days ago, and it's already been replaced. And who knows at what when, I don't even know when 31 will be up there. Okay, so if you if you click on it and you get this broken link, all you have to do is up here, just edit the URL to the current version. Just edit it to the current version, and then download the current version, and then edit the script file to point to the newest version. Okay, and once you've got it on your computer, you can forget about it. You don't have to worry about updating it. They're just doing lots of little bug fixes. So the updates aren't major updates, and they don't have an up. I don't think their software updates itself. It's never done that for me. So once you've got it on your computer, you can pretty much forget about it. You can just keep using it. Okay. All right. So that's the only thing I can think of about the homework assignment that I know that's changed is the version of. Oh, here's a URL to. You can always go here and just pick what you want to download from there. This is all their downloads, but like here, this is the current version. This is the version that's at 30. The version at 29 is gone. Okay, and like this is where the symbolic link should be. Somewhere on this page should be a symbolic link to the most recent version. So that one link would point to whatever is the most current version. Most projects create a current version symbolic link, but these guys don't have one. Not that I can find on this page. And it's a little bit hard to read this because they're chopping off the names of the files. If you want to really know what file that is, you have to hover your mouse over there and look down at the bottom of the page to see what the URL is. It's kind of, it's typical open source stuff. Some open source projects are run a little bit better than others, but ImageMagick is definitely a really famous piece of software. It's a very often used, common piece of software. Just got some quirks in the way they distribute it. Okay, then we're going to start talking about adding interactivity to the renderer. We're going to start talking about renderer 2, either Thursday or the week after. So most of you probably have not done GUI programming, interactive GUI programming. So that's not really 3D graphics. Interactive GUI programming, this is interactive GUI programming right here. There's nothing to do with 3D graphics, but it's an important topic. I think everybody should learn in college something about GUI programming. So we're going to use renderer 2 as an introduction to Java GUI programming. Now, in the real world of today, not many people do Java GUI programming anymore. It was popular in the 90s, and then the internet and browsers took over and JavaScript took over. And Java GUI programming still exists, but it's, Eclipse is an example of a program that's written using Java GUI, but it's hard to get information about because it's not a big deal anymore. So like this is an older book that's very nice. Somebody took a book that they wrote in Java. It wasn't selling much anymore because it's an older book, so they made it available as a free book. The book book. See, it's been updated recently, so it's kind of, they're kind of keeping it up to date, but the book was actually written almost 20 years ago. Okay, but so it's actually a good reference to Java GUI programming. It's one of the few kind of good references to Java GUI. So their chapter 13 is on graphical user interfaces. So we're going to talk, these first few sections here. That's mostly what we're going to be doing. Those first, about half the chapter, okay, up to the Java event model. That's what actually what we're really interested in. What we're really interested in is the Java event model. Okay, all right. So this is a pretty good reference. I mean, it's dated, but at the same time, Java GUI programming is dated, but it's fundamental. The Java GUI system is no different than JavaScripts or C++ or C's or Windows, or it's everything's pretty much Android. Android's a Java GUI system. They don't use they don't use the library that's built into Java. What we're going to use is this library is built into Java. Okay, so that's what we want to use. We want to use with what comes with the JDK. An Android phone is a Java GUI system, but it's using the Android libraries. But they're not that much different than this. If you learn this, you can deal with anybody's GUI system. Okay, they're not all that much different. So if you learn one, you pretty much are learning all of them. And since we're writing the renderer in Java, we might as well just use the Java GUI system. Okay, I wish there was more about it, but this is a good reference. I mean, this one's pretty good. And here's the Java tutorial people have their own. Oh, I'm sorry, not that one. The Java tutorial people have their own stuff about the Java event system. I never thought the Java tutorials were all that well written, but they are pretty complete. I mean, everything you'd want to know is in the Java tutorial. This is the famous Java tutorial. Everything you'd ever want to know is there. And it's more like an encyclopedia, and they have some nice examples. So it's not a bad place to learn. Okay, so there's where this is where the Java tutorial does the stuff on events. And then there's one other reference here. This is actually pretty good, but it's a real long web page. It's just one long web page. It's pretty complete, and it's actually pretty good. Though it may be it's a lot to read, but it might make a good reference. It's got some nice explanations in it. Okay, so and it's it's some professor's website at a university. The guy who wrote this, he has a huge amount of material up on his website. He writes about a massive amount of stuff, and he has this Java GUI tutorial. Okay, and it's pretty good. It really does explain what it is you need to know about Java GUI programming. Okay, so there's 3 references that we'll do lots of examples using the renderer as the base case. We'll do lots of examples with GUI programming. Okay, all right, then let's start talking about this projection and rasterization stuff. Okay, we want to talk about the algorithm that's in the renderer. Okay, so from the point of view of this file here, we want to start talking about what's in this box here. We've said a lot about the data structure going in. We've said a lot about the data structure that comes out. Now, what about the algorithms that manipulate this data structure to produce that data structure? Okay, so we're going to start talking about the algorithms. And at this point, there's really only 3 algorithms in there. The 3 algorithms are projection, rasterization, and clipping. And I gave you references for projection, rasterization. Clipping is, I couldn't find it's not that difficult. Well, the clipping stage is pretty straightforward, but I couldn't find a good explanation of clipping. So it's in the README. If you read the README, there's also an explanation of all this in here, okay? Or if you build the Java docs. It's a little bit nicer to read if it's formatted in the Java doc. Okay, so here it's formatted a little bit nicer. Okay, so we are starting to talk about the renderer. Okay, and we pictorially imagine a render. You'll see this if you Google the phrase. You Google the phrase graphics pipeline, you'll get gazillions of pictures of this idea of the stages of a pipeline. Yeah, everybody and his brother has drawn a picture where they represent the stages of a pipeline. These are the stages of the rendering algorithm. So here's a little picture of the stages of our pipeline. What goes in it are vertices, and what comes out is a frame buffer. And it's going to have right now 2 steps. A projection step of vertices, and a step that combines the rasterization and clipping. Later on, this will be broken up into 2 steps, and we'll see why it should really be broken into 2 steps. But right now, it's a combined rasterization and clipping step. And what you do is, remember the scene data structure is a camera, a list of models, and every model is a list of vertices and a list of line segments. Okay, right. What we're going to do is we're going to project the line segments and rasterize. I'm sorry, we're going to project the vertices and rasterize the line segments. And we want to get a sense of like that. That's how the thing is structured. It's project vertices, rasterize line segments, and that shows here is projection of the vertices, then rasterization of the line segments. Okay, so the idea. So let's do them one step at a time. Okay, so the vertices go into this thing and get projected. The projection. Remember, I had another reference for you that you can download. There's some pictures in a folder here. I'll just download it and unzip it. It has some nice pictures. Okay. This was, well, let's see. I forget which one it was, has. Well, actually, you know, I should just be using the reference I gave you for the reading. They have good pictures in here too. Okay. There's the, see, we want to project the red dots are the vertices. The blue segments are the line segments. We need to project the red dots over here. We need to get them flat before. The idea is to get everything projected into this plane so that we can then compute this image. So the first step is to get everything projected into this plane, which they call the canvas. Okay, and we're going to call it the projection plane. Okay, so I think they have another picture like that. No, okay, but that's our first step. Project the vertices. Now, I wish they kind of shown little red dots there too. So the 8 red dots here are going to project to 8 red dots there. And what we're doing is we're projecting the vertices, not the line segments. The line segments actually are not, you know, at this point, the line segments won't play any role. The line segments won't play a role until we get down here. Then we will rasterize the line segment, which means essentially fill in the dots between the red vertices. So the red vertices project down to here. And then after the red vertices projected down to here, then you want to draw that line segment that goes across. The render actually never has anything like that line segment in it. That line segment in 3D space kind of doesn't even really exist from the point of view of the renderer. The renderer just knows about these vertices. it projects them down to here, and then after it's projecting them, then it pays attention to the line segment. Okay. So we need to get everything from three-dimensional space into this, what we call the projection plane, or the, people have a lot of names for it, the image plane, the canvas, the projection plane. Okay, so people have a lot of different names for this. Okay, so we want to project down to there. And we saw in these pictures here that, you know, when you project down to here, things that are far away end up looking smaller. Yeah, and that's the whole point of the projection, is that this process will give us a 3D effect because things that are far away project smaller. And we'll see. See, we saw that in this picture here. Something A, as far A and B have the same height, but A projects to a smaller height than B projects to. So the projection of A is smaller than the projection of B. That's the key idea of 3D rendering. That's what creates the effect of these things. That's what your eye sees. Things that are farther away appearing to be smaller. Okay, so step one of the render is to project the vertices. Not, notice that this is not drawn as a bunch of vertices. It's drawn as a little stick figure. But that head would actually be a bunch of vertices. And this rectangle here would be 4 corner vertices. We're actually going to project the vertices, not the image. We don't project the image. We project only the vertices in the image. Okay? Okay? And here's the formula. Now, they also did the formula in their website. This formula is real simple. We'll just look at deriving it several different ways. Let me shrink this. What this picture is doing is it's making a simplified version from this 3D thing. You can't really reason with this 3D picture. It's a little bit too complicated. So you have to do like what mathematicians do a lot, which is to take a part of something and just emphasize one aspect of it so that you can write formulas that emphasize the one aspect of it. Okay, so what we're going to do is, instead of projecting three-dimensional space onto a two-dimensional canvas, we're going to project a two-dimensional space into a one-dimensional canvas. That's this picture here. And it was also this picture here. Notice that this picture helped because what it really did is it took away a lot of the overhead, and it just said the key idea is let's project this one-dimensional, well, this two-dimensional space onto this one-dimensional canvas over here. Okay. Now, if you want, you can imagine that this is really three-dimensional space where there's an axis coming straight out at you. Okay. So another way to think about this is it really is three-dimensional space, but I'm looking straight on one of the axes. Okay. Or you can just think of it as two-dimensional space being projected onto one-dimensional space. So that's that picture, and it's also this picture over here. Both these pictures, now this picture chopped it off even more. This picture said, well, this picture's symmetric. Let's just draw an axis through the half of this and just throw away the bottom half. We really only care about that point there being projected down to here. Okay, so that point there being projected down to here is that point there being projected down to there. There's the view plane, the image plane, the canvas plane, however you want to call it. That's the plane we're projecting onto. That's viewing. See, here he calls it viewing face. Here he calls it view plane. They called it canvas. Okay, everybody's got a different name for this plane that you, some people call it the film. It's like on a camera, that's where the film is. On a digital camera, that's where the CCD is, the charge coupled device is, the sensor. That's where the sensor is. So everybody's got, you always have this image here of this two-dimensional thing that you're projecting onto, but everybody's got a different name for it. Okay, so now, so we go from a three-dimensional picture, we simplify things from 3 dimensions down to 2 dimensions. And then even this 2 dimension, we can just chop off the bottom half of this, and we just say, here's what it means to project one point. That point there is a vertex into something that we want to project to the view plane. Okay, and then we want a formula for this point here. What we know is this point. This point's in our model, and we have this point's in our list of vertices in the model. So we know this x, y, z. We need to compute this. Okay, this view plane for us is going to be at z equals -1. Okay, here they just have it at some point z. We're going to put it at z equals -1. Here they don't even tell you where it is. Here they just say, oh, you're projecting forward to some plane here. The I is over here. See, the I is over here. That's 0, 0, 0. That's the origin of the coordinate system. So the I is here. The I is here. In this picture over here, see, the I is there at the corner where you're projecting from. Okay, so you've got these lines coming out of the eye, passing through the canvas and hitting a vertex. Okay, so you have a line coming out of the eye, passing through the view face, and hitting a vertex on your object. Okay, and same here. A line comes out of the eye, passes through the view plane, and hits our point that we're interested in. And we need to compute that point there. We know that point. We need to compute that point. Okay, and this is actually just turned out to be real simple algebra, because we know how to write the equation of a line, and we can solve for this. Actually, we don't even do it by writing the equation for a line. The best way to get the formula for this point x prime, y prime, is use similar triangles. Okay, use the idea from way back in pre-calculus of similar triangles. See, this triangle here, the outer one, and the inner one are similar because they have the same angle at the eye, and they're both right triangles over here. So they have the same angles, similar triangles have the same angles, but different sides lengths. So the 3 angles here are the same as the 3 angles there. So similar triangles. Similar triangles tells you that the ratio of this to this is the same as the ratio of this to that. Or another way to put it, any two sides, their ratios are the same. So the ratio of this side to that side is the same as the ratio of this side to that side. Now look at, that's what they wrote here. That's the similar triangle ratio. Now which one did they use? X prime is that height there. Oh, I'm sorry, X prime is, this is going to be the x-axis. You notice that they wrote x, y, z, but there's only 2 dimensions. Z is depth, and x is this axis. Okay, so y is coming out towards us. So they shouldn't have written the y here, because the y is coming. You don't see it in the picture. It's coming out towards us. Okay, so we'll take x is going up, take y coming out towards us, and z is depth. Okay, so x prime is that height. D is that length. So they're taking the ratio of that height to that length. But on the bigger triangle, that height, x prime, is similar to x. And this length D is similar to that length there. So they're using the 2 legs of the right triangle. They're saying that this leg is to that leg as this leg is to that leg. And they're not using the hypotenuse. They could, but in this case, the hypotenuse isn't what we're interested in. We're interested in this leg here. We want to solve for this leg here. We know this leg here. We know this leg here because that's our -1. We're 1 unit away from the eye. And we know this leg here. We know this long leg here because that's the z coordinate of this point. So this leg is the x coordinate of this point. This leg is the z coordinate of this point. This leg is -1 because we decide, in our case, D is going to be -1. The only unknown here is this leg, so we want to solve for x prime. That's the unknown. And if you solve for x prime, all you're doing is taking D over to the right. To solve for x prime, you just take D over to the right, and there's the formula. Okay, that's the projection formula. That computes the new vertex. The projected vertex is now at x prime -1. Okay, and then you do the same thing to Z. The Z, this picture, if you just want, you can relabel this to the y-axis, and then just do the whole calculation based on y. So you're just changing your point of view. If you think of it in three-dimensional space, you've changed your point of view of staring straight down this axis to staring straight down this axis. Okay, to make it a two-dimensional problem, you either stare straight down that axis or you stare straight down that axis. So you're either seeing the x-axis or you're seeing the y-axis. Okay, so you can turn this 3D picture into a 2D picture two ways by either labeling this x or labeling that y. So you get the same formula. You get the same formula. Okay, this formula here is the heart of rendering. Rendering 3D graphics is just that little formula there. And let me show you now. Let's switch to the code. Okay, go to the, not the homework assignment. Go to the render. Go to the pipeline package. And there's the projection stage. There's that stage that's, the first stage. There's the rasterization stage. There's the projection stage. Look at it. I do a little bit of ASCII art, and there's the picture. That picture is this picture again. Okay, so I did it using ASCII art. Okay, there's all the same thing. -1 is this D. There's the line coming out of the eye, seeing that point there. That point has X and Z coordinates. The C means camera coordinates. We're sitting in front of the camera, so we think of this as camera coordinates. We need to find that height there, the projected height. So we're given the camera coordinate of this point. We want to find its projected coordinate. So we want to send that point, we want to project that point down to there. Okay. And this formula here is that formula there, except I just have D is 1. That distance is 1. Okay. All right. And then you solve for him. Okay. And you get this formula here. Okay. Then that formula just gets put right in the render. There it is. Okay. The X coordinate of the projected point is the, I put the minus sign in here I had the minus sign in the numerator, and here I have the minus sign in the denominator. So I wasn't consistent. Okay. So down, it's the X coordinate of the original vertex divided by the Z coordinate of the original vertex. The X coordinate of the original vertex divided by the Z coordinate. And it doesn't really matter where you put the minus sign. Over here I had it on the numerator. Down here I have it written in the denominator. Over here, they have it written, see, in the denominator. Okay. They have so I wrote it down here the way they wrote it over here. Okay. And then you do the same for the Y coordinate. And then this point's Z coordinate is D, which is -1. So here is the new X coordinate. Here's the new Y coordinate. And here's the new Z coordinate of a projected point. Okay. All right. Now, we do that for every vertex in that model. So notice that I'm iterating on every vertex in the model, in the model's vertex list. Okay, so you pass to this projection stage a model. Okay, and then you iterate over every vertex in the model and you project the vertices. So that's what we were saying. You project vertices. I'm not going to touch the line segments in this stage. The line segments don't play any role. Notice that this picture says nothing about what that vertex is connected to. That's important. At this stage, I don't care if that vertex is connected to one other line, 10 other lines. I don't really, another way to think about it is, in this picture here, remember I said, in the render, you really don't even know about these lines yet. We're just going to project that vertex down to there without any care about how many lines connect to that vertex. Okay, right? So we're just projecting the vertex at the time of projection. We don't need to know anything about lines. Okay, so the projection stage doesn't touch the line list. It only looks at the vertex list. Now, the camera is in here to tell us whether we're supposed to do a perspective projection or an orthographic projection. See, here I should have, so here I'm going to do the orthographic projection, okay? The orthographic projection is just project straight back. So in the orthographic projection, you actually don't change anything. You actually just move from here to here. You just go straight back. If you look at our pictures, our little file of pictures, remember, orthographic projection just goes straight back. You don't really have to. So all you're doing is changing the z coordinate from what it was to -1. So all the z coordinates just get changed. So if you look at the code, same x coordinate as before, same y coordinate as before. And actually, I didn't project to -1, I projected to 0. A lot of times when we do a parallel projection, for quirky reasons, we project, instead of projecting into this view plane, we project into the 0 plane. Okay, so instead of projecting into this view plane here at -1, we just project all the way into the xy plane. Okay, and it doesn't really matter. I actually did it this way so that when you're in the debug, if you do debugging and if you use the render to debug, if you see a -1 in the vertex, that meant it was a perspective projection. If you see a 0, that meant it was a parallel projection. So it kind of helps distinguish between things that were perspectively projected and things that were orthographically projected. So I did it more just as a flag. Use -1. You are projecting into this -1 plane. So for the perspective projection, it kind of makes sense to put a -1 there for perspective projection. For the parallel projection, it doesn't really matter what number you put there. Okay. So I put 0 to make it just different than this number here. So parallel projection is back to here. Okay. All right. So the projection stage needs to know what the camera says. Is the camera saying parallel projection, or is the camera saying perspective projection? So that's just a Boolean. So if the camera says perspective projection, do this calculation. And if the camera says do a parallel projection, do this calculation, which isn't much of a calculation at all. All we're doing is replace. Actually, this is kind of a waste. You could just delete this code and it would all work, because you're not really updating. You're just copying x from one vertex to another vertex. Okay, I left it in there just to emphasize that there is a projection idea, that parallel projection does these formulas and perspective projection does these formulas. But if I was trying to optimize this code to be as fast as possible, this code doesn't really do anything. It just copies a vertex from one place to another. Okay, right? Then this stage has updated the vertex what it's actually doing here is it's creating a new vertex list. See up here, because we need to create new vertices. This vertex needs to be replaced by that vertex. In this picture here, these 8 vertices need to be replaced by 8 vertices in here. So we're going to create a new vertex list. We create an empty vertex list, and we add to the new vertex list these new vertices which have the updated coordinates in them. So I'm getting these values out of the old vertex and putting them in a new vertex. So I'm iterating through the old vertices. So I'm iterating, if you think of in this picture, I'm iterating through these vertices. So that's this iterator here. And for each one of these vertices, I calculate this vertex and put it in a new list. So these vertices are being put in a new list. So use the old vertex V, to compute the coordinates of a new vertex, add the new vertex to the new vertex list. Okay, notice a lot going on. Adding a new vertex to the new list. Okay, at the end, I want to replace the vertex list that was being used with the new vertex list. And I do that by returning a new model that holds the old line segment list, the old name, and the old debug variable, but holds the new vertex list. So what the projection stage does is it gives you back a new model. It basically, so what it does not do is it doesn't modify this model. This model is left alone. And what the projection stage produces is that model there that's been smashed down into 2D. Okay, so it returns a new model that where all the vertices have been smashed down to here. Okay, so that's kind of an interesting idea. We don't mutate this model, we leave it alone. We create a new model that has all the vertices smashed down to here. Okay, right? So that's how the perspective projection works. Notice if you look at the signature, the projection stage takes in a model and it returns a model. And the new model, you can see from here, the new model is the same vertex list as the old model. The vertex list just go the line segment list. The line segment list just goes along for the ride. It's not really used. It's going to be part of this new flattened model. The flattened model has the same line segment list that this one did. Okay? So all that stuff is copied from the old model to the new model, but the new model has a new vertex list. Okay? All right. Okay, so that's the first stage of the render. You project the vertices. Okay. The next stage is actually a little bit tricky. Oh, if you notice, this stage wasn't very much code. The projection stage was, literally, I could write that as one line of code. If I didn't want to, use a lot of indentation, that's literally one single statement. Okay, so if you include the fact that I'm iterating over that vertex list, yeah, it's just a few lines of code. Okay, it's really simple. On the other hand, the rasterization is going to be quite a bit more code. The rasterization is all this code here. Okay, rasterizing is more complicated. Okay, rasterization is definitely a much bigger. Your graphics card, your GPU has way more stuff inside of it dedicated to rasterizing than it does to projection. Okay, rasterizing is a big part of the render. So it's the harder thing to talk about. Okay, so let's start talking about the next step. Okay, so if we go over here to, oh, I'm sorry, we just talked about this step, the projection step of vertices. Okay, so now all our vertices are in the image plane. So we've taken vertices that were in camera coordinates, three-dimensional space, and we smashed them down to vertices in two-dimensional space. So we're almost ready to draw a picture. We've got everything smashed down to a plane. The frame buffer is just a two-dimensional plane. So this image plane is very close to this frame buffer. And the rasterizer is the bridge from this image plane to the frame buffer. Essentially, we have to take what's in the image plane and figure out how to turn on pixels in the frame buffer. Okay, now let's see, can I get this to fit? Not quite. Here is that image plane. Okay, so here's the y-axis, the x-axis, the z-axis is coming straight out at us. But we don't care about the z-axis anymore because we've pushed everything into the z equals -1 plane. So this box here is the image plane, and this box here, well, this is the image plane, the xy axis is the image plane. This box here is what the camera can see. Remember, the camera has a view frustum. The camera has a view, well, actually, this one doesn't show the view. Oh, they don't have a picture of the view frustum. So let me go to the other pictures. Okay. The camera has this view frustum, right? Okay. It only sees what's inside that rectangle at the front. If something is outside that view frustum, it's outside of that rectangle. So they call that the clip plane here, okay? So you can see how they projected this image into that rectangle. That rectangle there is, for us, this rectangle here. We're going to call that the view rectangle. So the view rectangle is what the camera sees. If something slides to the over this way, at some point it'll slide out of that view rectangle. It'll be out here from our point of view. The camera sees what's inside here. Okay? Okay. Same kind of idea here. This is the view rectangle here. This is the view frustum. The view, you project everything to the front of the view rectangle. Here he's got it drawn over here. There's actually the view rectangle. So this rectangle here is our rectangle here, but it's also, you can think of it as this rectangle here. If something slides off to the side here, it will leave the view rectangle and we won't be able to see it. Okay? All right? So okay, so that's one of our main ideas, is that we have this view rectangle, and this is the part of the view rectangle that you can only see, you only see things that are inside here. So this view rectangle becomes the viewport. This rectangle and this rectangle are supposed to be the same. I mean, I couldn't draw them to be they should actually be like, they're not the same size, but this corner is that corner. This corner is that corner. This corner here is that corner down there, and this corner here is that corner down here. This is the viewport in the frame buffer, and this is the view rectangle in the projection plane. If an object's sitting in here, that means we should turn on pixels to show it over here. We have to somehow take objects that are over here and turn them into pixels over here. Now, what's really over here are just vertices. You know, we'll have a vertex here and a vertex here and a vertex here. So first we'll need to do is find a formula that takes a vertex from here and figures out which pixel it is over here. Okay? So we need another formula now. Earlier we had a formula that projected onto the view plane. So we had a formula that projected to the view plane. That was this formula here. Now we need another formula that takes a point in the view plane. So we project it to the view plane. So now we've got points in the view plane. We have to figure out, okay, if you got a point in the view plane, which pixel is it over here? Okay, so we need a formula that converts converts vertices in the view rectangle into pixels in the viewport. Okay. After we've got, now remember, we've got vertices over here. We haven't said anything about line segments yet. Like there's two vertices over here and there's a line segment connecting them. Once we get the left vertex to a pixel over here and the right vertex to a pixel over here, then we'll figure out which pixels go in between them. That'll be the last step. So we project a vertex to here. Then we take the vertex, which puts it in here. Then we take the vertex and move it over to here. And we take the other vertex in the line and move it over to here. And then we figure out what pixels are between there. And if you go back to the web page here, they kind of do this. They kind of show this picture down here. Oh, I'm sorry. I lost. In the other page, in the rasterization page. Okay. I mean, here's a nice way to think about it. You can think this thing here, you can imagine it as being the same thing as this thing here. That's the canvas. Okay, see, you project to the canvas. You project to the canvas. But here they chop the canvas up into pixels. That's actually this idea that this view rectangle here really kind of has this thing sitting almost on, they're really the same. You can imagine this thing as being laid on top of this thing. So you can imagine that this view, this canvas here actually is the frame buffer where, and you can imagine this really filled with little pixels. So a lot of times people draw it this way to combine the idea that that's what you're projecting onto. That's the view rectangle. But the view rectangle is chopped up into pixels, though it really isn't. The pixels are down here, the view rectangle's up here. They're really separate ideas. And this is one of the things that makes it a little bit tricky. There's a blurring between these two things here. In fact, some people call this one the viewport, and people call this the viewport, and they call this the viewport. I call this one the logical viewport, and I call this one the camera viewport. You know, they are what the camera sees. This is the image rectangle that you project onto. This is pixels. The big difference between them is a point here has decimal number coordinates. Like there's a point here that has coordinates 1.5 or 0.7. Okay, so notice that this number here is 1, 1. So a point here would be like 0.5, 0.3. This is a frame buffer. The coordinates here are integers. Well, actually, the frame buffer is down here. The coordinates here are integers. Okay, the coordinates down here are integers. This is actually going to be an intermediate. This picture here is, since this picture here where you've laid the frame buffer on top of the view rectangle. Okay. So we're going to do this in a sequence of steps. We project to here. We get points in this square that goes from -1, 1 to +1, 1. We're going to figure out where those points are in a logical viewport. Notice that the logical viewport is this. What I'm going to do over here is still use decimal numbers. Okay, so this lower left-hand corner is kind of weird. It's 1/2, 1/2. And this upper right-hand corner is width plus 1/2, height plus 1/2. That's this corner here. Okay. These dots in here have integer coordinates. That dot there is 0, 0. That dot there is 1, 0, 2, 0, 3, 0. This dot here is 0, 1, 0, 2, 0, 3. Those dots are what are called logical pixels. Okay, these dots are called logical pixels, and there are H of them going up this way and W of them going out this way. This is the frame buffer. The frame buffer is little squares. The frame buffer is actually physical pixels. These are little boxes. Over here, there's no little boxes here. There's little dots. There's dots called logical pixels. Down here, there are squares called physical pixels. You think of each one of these dots as being the center of one of these little squares down here. So that dot there would be thought of as the center of this pixel down here. Okay. This pixel up here you would think of this dot as being its center. This dot has coordinates 0, H. Okay. This pixel has coordinates 0, 0. There's a funny flip of coordinates over here. This stuff can get real confusing real fast. The frame buffer has 0, 0 in the upper left-hand corner. This guy's got 0, 0 in the middle. This guy's got 0, 0 down here. This corner is this corner, which is this corner, but we're using different coordinate systems. This center is this center, which is this center here, but we're using different coordinate systems. In this coordinate system, that center is 0, 0. In this coordinate system, 0, 0 is that pixel there. So that center is not 0, 0. That center is that point there, should go to there. Whatever the coordinate is there, that's what that point is there. Over here, the origin's up in the upper left-hand corner. Okay. This origin is not that point, and it's not that point. They're different coordinate systems. So this 0, 0 here should go to the middle of this picture here, and it should go to the middle of this picture here. Our transformations have to make sure of that. Okay. This corner is that corner. You know, lower right-hand corner is lower right-hand corner is lower right-hand corner. Center is center is center, but it's weird because the coordinate systems are shifting all over the place. And you can see origin in the middle, origin in the lower left-hand corner, origin in the upper left-hand corner. Okay. This is the view rectangle coordinate system, the camera coordinate system. This is going to be called the logical pixel coordinate system. And this is the pixel coordinate system, the viewport coordinate system. This is the viewport coordinate system. Okay. We have to write formulas to move from here to here to here. Okay. And we have a vertex in here because that's what our projection stage gave us. We're going to transform that vertex over to here. And then we're going to transform that vertex over to here. This stage here is here to make our life easier, even though it doesn't seem like it would be. This stage is really here to make our life easier. Without this stage, we could go directly from here to here, which is essentially what this picture over here kind of does. There's these little boxes here are these little boxes down here. Okay, so they're showing these. Now, these little dots here, see that red line? It goes through the middle. What you're supposed to do is you're supposed to take a red line, a line that goes from the eye through the middle of one of those square boxes and see where it goes over here. Okay, so the red line, we call the projection line, goes through the middle of one of those boxes. That's these points here. These points here are the points that the projectors go through. So this picture, and this picture are all blended into this one picture. Okay. This picture is this outer rectangle here. This picture are the centers of these little squares here. Each center is one, the center of one, each of these squares is just one point. That's what we call the logical pixels. These little boxes here are these little boxes here. Okay. These little boxes here and these little boxes here are not dividable. They are the unit. So what you have to do is you have to figure out what color does that square become? What color does that square become? So now up here, there's no little boxes here. That point there, what we're going to do is we're going to try to figure out what's the color at that point and then make that appropriate box down here that color. But it turns out to be a little bit more complicated than that. It doesn't quite, that's kind of what you think is happening, but it doesn't turn out to be that simple. But in a sense, what you're really trying to say is that red line goes through the middle of a square and hits something over here. The color of what it hits over here is what the color of that whole square should be. Okay. And that's more or less what we're going to do. We're going to just assume that whatever the color of that dot is, we're going to make the color of that square that whole same color. But what if you're on the edge? What if you're really on the edge of something? See, like right here, notice that square, maybe it shouldn't be green. That the center it's green, but it's not green here. So you might say, but that square shouldn't really be green. It should be something like something halfway between green and white. Okay, and that's one of the ideas that eventually we have to deal with. That's called anti-aliasing. That maybe this square here, this square here, solid green. You pass a line through here, but it's inside the triangle so much that whole square is inside the triangle. But over here, that square is actually not completely inside the triangle. When you shoot a projector through there, it hits the edge of the triangle. So the projector hits the edge of the rectangle. Well, that's green. You hit a green dot on the edge of the triangle, but that triangle doesn't cover the whole pixel. So you have to kind of wonder if you really should make that pixel square. Should you make that pixel all green? If you do make it all green, you get, oh, they don't show it here. When you do make it all green, that's when you get pixelated pictures. Let me show you an example. You get these pixelated pictures. Somebody wants to draw that curve. These little boxes are the pixels. Any one of those boxes can only be one color. So even though the curve kind of is a thin line through these boxes, you're forced to draw big, you're supposed to fill in the whole boxes and you get these pixelated pictures. Okay? So that's a problem we're going to have to deal with, is that what do we do when we're on the edge of one of the, what do we do when something should really be on the edge of a pixel? This picture here is another example of what we're talking about over here. These circles are these dots. This space, it's kind of weird the way he drew this. He's got squares here, but those squares aren't these squares. In this picture, the squares would go like this. There'd be squares around the dots. The dots are the pixels. That's these guys. The thing you color in would be the square around it, which is not, I don't know why he put the square like this, okay? Notice that you have a problem that a line can go from one pixel to another pixel and never hit any other pixel. See, there's a pixel, so I mean, I could have a line that goes from this dot to some dot down here, but the line could actually maybe pass through mostly white space and never touch another dot. It's not that really hard to do that, to come up with a line that goes from one pixel to another pixel and never touches another dot. Notice that it never goes through. See, it misses that one. It missed the point where the dot really is. The dot's really at the intersection of those lines. So it missed that one, missed that one, missed that one, misses that one, misses that one, and hits this one. Okay, so if that's your line, what other pixels are on that line? What we're going to do is we're going to say, well, we missed that pixel and we missed that pixel, but we're closer to this one, so we'll draw this one. We missed that pixel, but we're pretty darn close to it, and we're pretty far from that one. Even though we missed this pixel, we'll turn it on. And we go down here. Well, we're a little bit closer to that pixel than we were to that pixel, so we'll turn on this one. Now we're closer to that pixel than that pixel, so we'll turn on this one. So we turn on the pixel we're closer to, but that ends up giving us these jagged lines. That's what happens. You end up getting jagged lines. I don't know if he didn't really draw a picture of the jagged line. Okay. So that's what we're going to be doing. Let me see if there's another picture in here. There. Okay. So you go from that pixel to that pixel. Now, see, this picture again combines this with this. The dots here are the dots here, but that's the logical viewport. The little squares here are the little squares here. That's the viewport. So he's combined them into one picture. Okay, but there's really two pictures here. One coordinate system has the dots in it. That's the logical viewport. The other coordinate system has the squares in it. That's this. The squares are the viewport. The dots are the logical viewport. The line goes from that pixel to that pixel and doesn't hit any other. Well, it hits that one pixel there. You know, it misses most of the other pixels. It misses them. It does hit one pixel. Okay. So what do? You say, well, I have to turn on. I can't just turn on this pixel this pixel, and that pixel, there'll be big gaps in the line. I need to turn on pixels all the way across. If you're in between two pixels, you pick the one you're closer to. If you're in between two pixels, the line is in between two pixels, pick the one you're closer to. Okay, so that's what he ends up doing here. He goes from here to here, and he picks the pixel that he's closer to. Picks the pixel that he's closer to. Notice that you get a line that's kind of weirdly stair-stepped. That's called pixelating or aliasing. Okay, all graphic systems do that. And remember, when we used the magnifier, we saw these pixelated. Early in the semester, when we magnified things, we saw that everything's kind of jagged. When you blow things up, you see the stair steps. You see them in everything if you magnify it enough. Now we're actually worried about picking the pixels on that stair step. We need an algorithm that picks those pixels. Given that end and given that end of the line segment, we need an algorithm that finds those pixels in between. Okay, so that's what we're building up to, is the algorithm that's going to take that coordinate and that vertex at that endpoint and that vertex at that endpoint. Those two vertices will be in a line segment, so we know that that's a line segment because these will be two vertices we projected, but we have a line segment data structure that says there's a line segment connecting this to this. So then we have to find the pixels that go from there to there. Okay, all right. Now let me close these. Okay, that's the idea of what we're doing. Okay, so we start with projection. We project to the view plane. Then we start doing some calculations. We have points in the view plane. We transform them into points in this logical viewport, which is sometimes called the pixel plane, where these points are pixels, but they have the same coordinates as the viewport. Okay, so these are points in a plane with decimal number coordinates, but the points are integer coordinates. Like that is the coordinate 1h. Okay, it's got integer coordinates, but the points in between it have decimal coordinates. Over here, there's nothing in between that box and that box. Okay, it's real important. This box has integer coordinates and this box has integer coordinates. There's nothing in between those two boxes. This point has integer coordinates, and this point has integer coordinates, but there's stuff in between them. We're going to plot a line here. The line is usually going to be in between these points, and then we need to figure out which one of these points we're going to associate to the line, and that's when we point pixels down here. Okay? Okay? All right? So let's see, how much time do we have left? I forgot to set, we got 5 minutes left. Did I lose track of time? We have 5 minutes.
Yeah, 5 minutes.
5 minutes, yeah, okay. I usually have a timer set, and I forgot to set the timer because otherwise I don't have a clock in front of me. Okay, all right, all right. So the projection stage was the easy stage. The rasterization stage is really tricky. Because there's this picture, this picture, and this picture, and there's a lot going on. The rasterizer seems tricky. Okay, now if you look at the rasterizer code, the rasterizer code. Okay, here's the three things here. Points are in the view plane. That's what they got projected to. They're in the view plane. We want to figure out from here down, we want to go from here to here. We want to go, what pixels do we paint in the viewport? But instead of going from here to here, we actually go from here to here to here. We take points in here and we send them to points down here. This is essentially a version of the viewport that's got a dot for the center of every one of these squares, but we can work with decimal numbers down here. We work with decimal numbers down here. We work with only integer coordinates over here. Each one of these boxes is just an entry in an array. It has integer coordinates. There's nothing in between them. Okay, we need to go from here to here. We need to take a point in here, send it to a point down here. Once we've got a point down here, that's one vertex in a line segment. We got another point down here, which is another vertex in a line segment. Then we have to figure, then we've imagined the line going from here to here. But the line from there to there will miss vertices. It will miss pixels. It will fall in between the pixels. And then we ask ourselves, well, which pixel is it closest to? Which pixel is it closest to? Okay, so the algorithm works like this. Okay, this step here is the calculation of the points in here. Okay, what I'm going to do is I'm going to rasterize, let's start from the beginning. I'm going to rasterize a model. Okay, and actually what I'm rasterizing is a line segment in that model. So I'm rasterizing one line segment from that model into that viewport. So I'm going to do this one line segment at a time, okay? So the line segment has two indices in it. Those two indices tell me what vertices to get out of the model, okay? So that's this thing right here. I grab two vertices out of the model using the indexes in the line segment. That gives me two vertices over here. Okay, so I start with a vertex 0 and a vertex 1 up here. And I know that they're the endpoints of the line segment. Okay, so I'm given a line segment in a model and I need to paint pixels in the viewport. I start by grabbing the two endpoints of the line segment. And they are these are projected points in the view plane. Okay, right. Now I want to calculate where they go here. I want to calculate where they got sent to here. That's this formula. Okay. We transform the vertices to the pixel plane. Okay. We'll explain, let's see, we'll explain how these formulas are just simple. They're just mx plus b. Every formula is just a linear function. It turns out that everything is a linear function, but they're a little bit tricky to write. Okay, so we'll explain where they come from, but that formula sends me from here to here. Okay, then I want to calculate I have these two vertices here. I want to calculate the line, the equation of the line that connects them, y equals mx plus b. So I'll need the slope of the line. Okay, now, okay, we run out of time. Here, let me just show you one last trick we have to worry about. This is the next step in the code. There's a weird little thing we have to worry about. Oh, let's see. Here. Suppose I'm rasterizing that line. Looks okay. I'm walking from left to right, and I'm saying, well, I should turn on that pixel, that pixel, that pixel. Oh, I've gone up a little bit, so I should turn on that pixel, that pixel, that pixel. Okay. Now look at this line here. If I rasterize it by walking from left to right, I will paint this pixel, then I move over, and I have to paint that pixel, then I move over, and I have to paint that pixel. And I realize something's gone wrong here. Does anybody see what's wrong with this line here? What should I do when I rasterize that line? Can we see what I should do differently? How should I treat this line differently than that line?
Move up and to the right.
Pardon me?
You have to move up and then to the right.
Right. Yeah, I have to move up and to the right, not move right and up. See, here I'm doing like you do in calculus, y equals mx plus b. X over and up, over and up, over and up, over and up, over and up. This is y equals mx plus b. Over here, I'm supposed to go up and over, up and over, up and over. I have to write this as x equals m times y plus b. I have to turn my equation of a line. I have to invert it. I have to find the inverse equation of the line. The line is a function of x here. The line is a function of y here. We have to find the inverse equation of the line because we really should be going up and over, up and over, up and over, up and over, not over and up, over and up, over and up. So in the code for the rasterizer, we have to make a test of whether the slope of the line is less than 1 or the slope of the line is greater than 1. There's kind of the 45-degree line is a dividing line. For 45-degree line, it doesn't matter which way we do it. But if you're less than 45-degree slope, you should go over and up. But if you're more than 45-degree slope, you should go up and over. So that's one of the reasons why the rasterizer is kind of long, is because it's got two big cases to worry about. Then there's going to be other cases to worry about. So right away, you have to worry about whether you're rasterizing horizontally or rasterizing vertically. Okay, so as we step through the code, we'll see that we have to, that there's geometric pictures that explain why the code does different things. And we'll see that the code does funny things, but the answer to, you can't put pictures in your code. It'd be wonderful if you could put a picture like this in the code and say, the code does this funny thing here because of this picture. Well, you can't put pictures in code, so you have to like put a lot of words in the code, but we can still look at these pictures. So the code has these funny things where it does if statements that are checking for funny things because it's, well, one case is trying to find out, is the line like this or is the line like that? Okay, so there, again, last thing, to follow what we're doing, you need three things. Read these 2 pages. Then there's the renderer code itself. And then there's this folder I have here just called rendering, which has got a lot of I put a lot of pictures in that folder because I think those, I tried to, I mean, these pictures are everywhere on the internet, but I just tried to find some that I thought were good. Actually, I probably should update these pictures. I haven't gone through and seen if I can find better ones. Pictures for projection, pictures for rasterizing, and a few pictures for clipping. So I tried to just put pictures I thought were helpful in there. If you actually find good pictures, let me know, because it's great when I can find, I think, a really helpful picture of these things. So I've put some pictures in here, and there's lots of little ideas to draw pictures of. There's lots of little ideas that need to be explained. So the documentation is in the web pages I referenced, the code itself, and then these pictures. Okay, so we stopped there. Okay, on Thursday we'll finish talking about the rasterizing, and we probably won't start the GUI stuff yet. Yeah, we probably won't start the GUI stuff on Thursday, but we'll see. We'll probably finish the rasterizing code on Thursday, and then start the event stuff next week. All right, if you got questions, send me an email or come to office hours. And so run out of time, so I will. Does anybody have a question they want to ask real quick? Anybody have a last question? Okay, I'll go ahead and let's see. Okay, I think I stopped sharing. So I'll go ahead and end the meeting. See you on Thursday. Bye.